Hello and welcome to tonight's stream, and we are continuing from where I left off in Calculus Volume 1. But first, a little bit about the book. This is part of the OpenStax initiative of Rice University, and it's part of Creative Commons, so download the book in the video description. It's free. I have a physical copy. My physical copy is very nice. I personally like having physical copies, but if you download it and when we get to the questions part, you could actually look in the back of the book and know if I'm getting it right, and you'll know before I do. So let's get into it. We're continuing with the reading right now. All right. Just give me a second to get into it. Okay, here we are. We are continuing from page 20, combining functions. Now we have reviewed the basic characteristics of functions. We can see what happens to these properties when we combine functions in different ways, using basic mathematical operations to create new functions. For example, if the cost for a company to manufacture X items is described by the function c of x, so this is, we are in 1.1. And so we're going to say c of x is cost of x items. All right, and then we have, and this the revenue. So that's going to be r of x. These are two functions. So now the profit is equal to p of x is equal to r, let's just use small r of x. So the revenue minus c of x, the cost of manufacture, okay? Alternatively, we can create a new functions by composing two functions. For example, if we have, let's try this now. So we have this function, f of x is equal to x squared. And we have g of x, which is equal to 3x plus 1. Okay, and then we're going to say the composite function is called f, the circle of g, and that's defined as this. So the composite function f of g is equal to f of g of x, which is equal to the f of g of x, which is equal to g of x squared. So in this case, and the reason why it's squared, our f of x, so f of x is defined as x squared, and our g is defined, g of x is defined as 3x plus 1. So we take the f of x, we take the g of x and we wrap f of x around it to create a composite. So 3x plus 1, and we're going to wrap that inside there like that. That's going in there. So squared. So now, squared. So essentially, yeah, this g of x becomes the x of f of x. All right? And so, yeah, that's how we get that composite function. And so And that's where we have that's f of g of x. So in other words, and if you write, now we could also go the other way. We can do a composite of g of f. And to do that, we're going to have g, and we're going to compose it of f, which is going to be g. And inside of that is going to be f of x. So that's going to take, we're going to take our g of x, which is going to be our 3x plus 1, and that x, this becomes, we're going to drop the x squared inside of that. So it's going to be 3, and then we're going to have, first we're going to write the g of x. Actually, let's find 3x plus 1. So basically, the reason why it's squared, we took our g of x, which is equal to 3x plus 1, and then we inserted inside its x the f of x, which is equal to x squared. So essentially, the 3x got replaced with an x squared. So it's 3x squared plus 1. Okay, that's how we got it. Okay. And yeah, so remember, the combining g and f and g is not the same. You get different results. Okay, so now combining function with mathematical operators. To combine functions using mathematical operators, we simply write the functions with the operator and simplify. That's pretty good. So let's say we want f plus g, right, of x, and that's going to be f of x plus g of x. So we have f of x is going to be x squared plus g of x, 3x plus 1. So that's it, basically, x squared plus 3x plus 1. All right? And if we wanted to go f minus g of x, so that's going to be the same thing as f of x minus g of x. So we're going to take our f of x, and we're going to put that in here, x squared minus 3x plus 1, which is going to be x squared minus 3x minus 1. Okay, because the negative carries into both of them. And then if we have f times g of x, which is equal to f of x, g of x, they're multiplied by each other, which is equal to x squared times 3x plus 1. And that's going to be 3x to the third power plus x squared. All right? And f divided by g of x is equal to f of x over g of x for g of x not equal to 0, because if it is, then it's dividing by 0. So real quick, that's going to be our f of x is x squared over 3x plus 1. So yeah, that's basically it. All right. Now let's go through some examples, which we just did, but let's go some more examples. Yay, I like examples. All right. We have f of x is equal to 2x minus 3, and g of x is equal to x squared minus 1. All right, let's find f plus g of x. All right, so we're going to take our f, 2x minus 3 plus x squared minus 1. All right, so that in that case, it's going to be x squared plus 2x minus 4. All right, and Now, and also while we're at it, we're going to find a domain of this. So the domain, it can be negative infinity to positive infinity. So the domain is the input. Is negative infinity to positive infinity. We can use any number in this thing, and we're going to get a valid result in R, in real space. Or not R, in the real set of numbers. Okay, next, technically this would be an R2, because the way we're graphing this, this is going to be, can we have the x squared plus 2x? Actually, not necessarily. Let me think about this here. No, it wouldn't necessarily be an R2, but whatever. We're going to stick to the real set. Now, in R2, I was referring to, I mean, if we're putting in a graph, this is considered R2, and this is considered R3, basically. So R2 is X and Y, and R3 is X, Y, and Z coordinates systems. All right, but we don't have to worry about that right now. That's Calculus 3 stuff. Calculus 2 is a little different than Calculus 1, and then Calculus 3 builds on a lot of things from both. Okay, so we have f minus g of x. So we're going to subtract them. So we're going to take our f, 2x minus 3. We're going to subtract x squared minus 1. So we're going to have 2x minus 3 minus x squared plus 1. Okay? And just a second, I got to plug in my laptop. And I'm back. Okay, so I had to plug in one of my laptops. We have 2x minus 3 minus x squared plus 1. So yeah, the negative carried over. That's negative x squared plus 2x minus 2. Okay, and this one, the domain and the range, again, we're going to range from negative infinity to infinity. Any number, infinitely negative, infinitely positive, or in other words, any number, however big or however large or small you want it, negative or positive, we can do it. So that's fine. Nothing about these operations. Squaring it and making it negative, and then multiplying it by 2 and minus 2. These are all valid operations. Next, we have f times g of x. All right. So for this operation, we're going to multiply the 2. So we have 2x minus 3. And then g is going to be x squared minus 1. So multiplying this out yields 2x to the third power minus 2x. And then it's going to be minus 3x squared plus 3. And let's organize this. Okay, minus 2x plus 3. All right. Again, our domain is negative infinity to infinity. We can use any numbers we want here. All right. And now finally, we have f of g of x. So now here we have our f, which is going to be 2x minus 3 over x squared minus 1. All right. Do we want to simplify this here? I mean, we could technically expand this, probably. Just thinking here. So, can we do that? So, if this is going to be a squared minus b squared, let's try this. So that's going to be a plus b with a minus b. Okay. Squared. Okay, so that case, and we're going to say let a be equal to x and b equal to 1. So if we wanted to expand this, I'm just seeing if we can do anything to simplify this. 2x minus 3. But what I'm doing here is also going to be useful for another thing in a minute. You're going to see what I'm doing. We have x plus 1, x minus 1. Okay, so, and the top, can I pull out 2x? I mean, I can pull the 2 out and make it x minus 3 over 2, but that doesn't really do anything for me. And I can pull out the 3, make it 2/3 x minus 1. Again, that won't do anything for me. I can't really simplify beyond this. However, well, what I can do is we can say that this is valid except such that x such that x is not equal to 1 or negative 1. Another way to do it, we can say x such that x is not equal to plus minus 1. And why is that? Well, notice that if x is equal to 1, we have x minus 1. So 1 minus 1 is 0. So regardless of what this is, although technically this would be 2, times 0 is going to be 0, and which is undefined. And of course, the same thing with the minus 1 plus 1, that's going to be 0. So as you can see, it can't be, it can be whatever. So when we write this kind of thing, when we say our domain, when we put a condition that it can't be plus 1, minus 1, or whatever, that means everything else is fair game. And that's all we care about. We can't operate in an undefined area. And division by 0 is undefined. So it's not legal under the real set. Now, if you look at, I don't know if it's legal in any form, but let me just think about this for a minute here. Now, did I have to unfold it like this? Not really, no. I could have just gone x squared minus 1, and right away, here's how you solve it. You take your bottom, whenever you have this, and you're going to say x squared minus 1, and then you make it, we want to know where it's 0, because that's the problem. So plus 1, x squared is equal to 1, which if we root it, it's going to be x is equal to plus or minus 1. Square root of 1 is 1, but because in this case, when we're taking off the square, we lose our knowledge whether it's positive or negative. It doesn't matter what number it is. If it's positive or negative, you square it, then it could be positive or it could be negative. So unless we specifically know what the number is, we have to assume that it can be either. So in that case, we write x plus or minus 1. So that's another way to do it. You don't have to. So yeah. So that kind of answers that. Let's keep going then here. And now, okay, this is a good one. They're giving us a 1.4. Check our knowledge. We're going to go with f of x is equal to x squared plus 3. g of x is equal to 2x minus 5. Find f divided by g of x. All right, and domain. Okay, so those are the two things we have to find. All right, well, let's see here. F, we have x squared plus 3 over 2x minus 5. Can we do anything with this thing? Can we unpackage it in any way to simplify it? Not really. I don't see any way. So we'll leave that as is. So if that is going to be our equation, now what is going to be our domain for that? So our domain, we need to know where 2x minus 5 is equal to 0, right? Because we can't divide by 0. And we're trying to find where it breaks down. So plus 5 divided by 2, x equals to 5 over 2. That is where. And let's just plug it in and see what happens. 2 times 5 over 2 is equal to 5. Minus 5 is equal to 0. So the domain is going to be x such that x is not 5 over 2. All right. So let's check real quick. It's 1.4. Check your knowledge. X squared plus 3 over 2x minus 5, and x such that x is not equal to 5 over 2. All right, yep, so far so good. Let's keep rolling along. All right, function composition. When we compose functions, we take a function of a function. For example, suppose temperature T on a given day is described as a function of time T measured in hours after midnight. Suppose the cost C to heat or cool a building for 1 hour can be described as a function of temperature, capital T. Combining these two functions, we can describe the cost of heating or cooling a building as a function of time by elevating C of T of T. And we have defined a new function, which is C of T. Okay, so let's actually start a new page here. So we have, we're defining C of T here, of T, which is equal to C of T of T. Now the small t, think of it as an x. So it's just like f of x, g of x kind of situation here. Okay. So here we go. This is called the composite function. We note that the cost of a function of temperature T is a function of time. It makes sense. Define this new function of cost of the temperature of time. It doesn't make sense to define it as temperature of cost because the temperature is not a function of cost. So the cost is affected by temperature. The temperature is not affected by cost. Temperature is not going to rise if suddenly the bills go up. Okay, it's controlled by the sun, so it's a function of the position of the sun in the sky, among other factors, of course. But that's the largest factor, is the sun heating the atmosphere. Consider the function f with a domain a and range b. Okay, so f, and we're going to say domain, which is equal to input, and a, and b is equal to range, which is equal to output. So we have our function f, and then we're gonna have function g with a domain d, which is equal to input, and E is equal to range, which is output. Okay, so now we have, and if B is a subset of D, so if the output here is a subset of input here. So in other words, what you put out from F goes into the input of D. In that case, we're going to say that a subset of D, then the composite function is going to be G of F of X, like this, and then which is equal to G, and then we have F of X. So we have our F of X, function F, which is here, and it gives us an output. And then that output becomes the input for our G. Basically, that's how you can think about it. G is the outer part because it needs the input from the function F. Okay? Okay. So here we go. Okay, so now for a composite function of G of F, we have, let's see here, we're going to give ourselves a domain, domain of F, and a range of F. Okay, so let's just try this. F, we're going to say domain 1, 2, 3, and the range of F is going to be 0 and 1. And then the domain of G is going to be 0 and 1. And then this is going to be, and then the range of G of F is going to be carried over from what this input gives us. And in this case, the output would be 4 and 5, for example. So basically, and they have a couple of other things where, let's see here. Yeah, okay. So we're not going to worry about this too much. Basically, we're just going to keep doing equations and it'll make more sense. But that's kind of the idea. The input of one becomes the input of the next function, and then that creates a final output, which represents the interaction between the two of them. Composition of functions defined by formulas. Okay, so we have, consider the functions f of x. So let's just do a new page here. We have, consider, here we go, right, wait a minute, f of x is equal to x squared plus 1, and g of x is equal to 1 over x. Okay? So, in that case, find g of f. We're going to merge this of x, and we want to know its domain and range. And we're going to say domain and range. Okay, so, well, let's see here. We have the g, and then we're going to say, so let's roll this back a minute. So we're going to have g of f of x. All right, in that case, we're going to take the g, and then we're going to input our f of x where its x is. All right, so because the f of x gives us the output, and that output goes into our input g of x, and then when we solve the full equation, that gives us our final output. Okay? So our domain is, let's see here. Can we use 0? Sure, we can. We can go with 0. But our domain is limited. We cannot do we cannot do -1 and 1. Let's see here. So let's find domain. So x squared plus 1 is equal to 0 minus 1 minus 1, which is x squared equal to -1, which is not possible. So cool. That is not possible under the reals. That is in the imaginaries. So our domain is going to be -infinity to infinity. We can have any number that we want here. Now for our range, our outputs is going to, the bigger the number, the closer this is going to get to 0. Because an infinitesimally small number, one as, let's see here, we're going to say 1 over x, limit of x approaches infinity is equal to 0. We haven't gotten that far yet, but basically, as x approaches infinity, it gets infinitesimally small to where it's 0, okay? So just as if, let's say, what's 1 over a billion? Let's say you're like, okay, let's cut up pizzas, right? If we can cut pizza 1 over 2, so each of us gets half. What about 1 over 4? Each of us gets a quarter slice of the pizza. 1 over 8, as no numbers gets bigger, you get smaller slices, okay? 1 over 10, you get a tenth of the pizza. What about 1 over a billion, okay? What about 1 over a trillion? You get a trillionth slice of a pizza. What about 1 over a quintillion, right? What even is that? Like, could you physically hold something like that in your hand? Would it make any kind of sense? No. So at that point, it is 0, essentially. That's how that works. So when we look at it, what we're saying here is that as x approaches, basically our range is going to be from, now what is the smallest whole number we can have? It's going to range from 1/2 to, what is the largest possible number we can have, right? So by largest, I mean, what is the smallest number this can give us, which is going to be 0, right? 0 squared. So the smallest, so our range is going to be from 0 to 1. So we're going to say from 0, 1. Our range, as I understand it, because what happens is if we go with a negative number, it gets squared, so it becomes a positive number. If we make x equal to 0, then it's 1 over 1, which is equal to 1. And any other number progressively makes it smaller, so we're going to range from 0 to 1. Let's see how I did there. At least that's my take on it. Now let's see what the book says here. Okay, yeah, it is correct except one thing. This is a limit as it approaches infinity. So it's not, it is open on 0. So in other words, it looks like this. So this is 0, this is 1. It's a hard one, but it's open on the 0. It gets us physically close to 0 as we can without actually being 0. Okay, and yeah. So yeah, I got that. Let me make sure. Did I get the other part? The domain. Yeah, the domain is a set of real numbers, so it's -infinity to infinity, which is also equal to R, the real set. Either one's fine. You can say it either way. And we got the range solved correctly now. That's good. Solving the equation for x. Now let's solve it for x. So the way we're going to do this is going to be 1x squared plus 1 is equal to y. And we're going to swap this with that. We can do that. That's 1 over y is equal to x squared plus 1. We're going to say minus 1. So that's 1 over y minus 1 is equal to x squared. Root. So that's going to be x plus or minus square root of 1 over y minus 1. So, and the expression, basically, if y is 0, hang on a minute. Let me roll this back for a minute here. Which implies if y is in the interval 0, 1, the expression of the radical is non-negative. Therefore, there exists a real number of x, which is, yeah, so on that interval. Now, wait a minute, x is equal to plus minus. So, if x is 1, so that's 1 over 1, that's 1 minus 1 is going to be, it is 0, square root of 0 is 0. So that's fine. And, all right, expression under the radical is non-negative. So, try this here. Okay, now, in case you're wondering, well, since y is ranging from 0 to 1, right? What does that actually do if 1 over, because remember, I want to prove to you that this is not going to give us a negative number, right? And you think, well, what if it's 0.5? Well, 1 divided by half, by 0.5, is going to be 2. In other words, there's 2 ways to get halves. There are 2 halves in 1. So the result here is going to be root 1, which is 1. And the same thing if it's a smaller number, 1 over 0.2, which is going to be 1/5. So that gives us 5. There's 5 ways of doing it, minus 1, which is equal to root 5 minus 1, which is equal to root 4, which is equal to 2. So you see how that works? Hang on a minute. Yeah, so basically, dividing something by a number less than 1 makes a thing grow bigger because that means you can get more of those pieces. So you have one whole piece, and you could say, how many quarters can you get? Okay, you can get 4 quarters out of it. You see how that works? But if you're saying, well, what about I want a double of the 1? That's 1 over 2. Well, then you can only get half. Anyway, just fractions. This should be pretty obvious by now. All right, carrying on. All right. Here we go. All right, just 1 second here. Okay. We're going to continue with our next example. All right. And this one is going to be b. And what was the b? We want to do, again, let's write down f of x is equal to x squared plus 1. G of x is equal to 1 over x. And now we want to evaluate g of f of 4, comma, g of f, and the input is 1/2. Okay, so the first thing we're going to do, we're going to write, let's do, which one are we going to do here first? So let's take the first one, g dot of, we're going to combine the two of x, and we're going to do, so the composition of g and f, and we're going to have an input of 4 for the x. So we're going to say the g function, and then we're going to say 4 squared plus 1. Okay? And in that case, we're going to carry that over, and we're going to put that over into this. Now we're unwrapping the g part, which is 1 over x. We're putting the 4 squared plus 1 in there. And now we're going to solve it all. And that's 1 over 16 plus 1, which is 1 over 17. Okay? And in this case, next, so that's the result. They're giving us, and we're not looking for domain or range because they're giving us the input. They're saying our domain is 4, our range is 1 over 17. We have input, output. Okay? So now we're going to do another one. The composite of g and f with an input of -1/2. Okay? So we're going to write g, and then we're going to take our f function, and we're going to put that, instead of x, we're putting 1/2 in there. So -1/2 squared plus 1. And instead of finishing that up, I'm just going to write the g function next. So that's going to be -1/2 squared plus 1. Okay? And let's do that. Now we're going to do it. So -1/2 times -1/2 is going to be 1/4. So that's going to be 1/4 plus 1 over 1. Okay? So, and that point is that, right. So that's going to be, now we have to do math. 1/4 plus 4, which is equal to 5/4. So now we have 1 over 5/4, which is equal to 4/5. Okay? Remember, if you have a situation like this, where you have in the denominator a fraction, that is the same. So look, 1 over x over y is the same thing as saying y over x. So that is the same kind of situation. And so yeah, the fractions get flipped around. But getting back to what we're doing here, so that's 4/5. And again, what is our domain is 1/2. What is our range is 4/5. Okay, now, so we did that, B. Let's do C. We have, now again, our f function, x squared plus 1, our g function, 1 over x, and then we have the composite of f and g and of x, and we want to know the domain, and we want to know range. Okay, so we have the f function. We have, so f of g of x, which is equal to the f function, and inside the f function we're going to have, so it's going to be, there we go, and squared plus 1. Okay, so that is going to be, so notice we have the f function, and wrapped inside the input, the x, the g function. All right, and then the result of that is going to be 1 over x squared plus 1. Okay, so we want to know what is our domain, x squared, so plus 1, and in this case, well, we can't divide by 0, So our domain, it could be anything, but it can't be 0. Because if it's 0, we're breaking the rules. Even though technically we would still have a 1 on the outside, division by 0 is not allowed in any portion of the equation. So we can say domain X such that X is not equal to 0. Other than that, anything goes. Any number that we can go, any large number, small number, except, again, as it approaches 0, we cannot have 0. That's the only thing. So that's the rule. And so let me check that real quick here. Okay. Yeah. The domain is the set of reals such that X is not equal to 0. Now, let's find the range. So to find the range, basically we want to know what is our valid output. The range should be, okay, so we are going to go from, it's going to range, right. So if we are going to say, what is the smallest number we can get here? Let's say for a minute that what happens if we can go, we can almost have 1, right? We can go a super duper small number, but not 0. Let's say 1 over 1 million, right? Very, very tiny number plus 1. It's going to be like 1.0000001, something like that, right? Almost 1. And yeah, so basically, so we're saying that that's almost 1, right? But, and we could add a lot of zeros onto that. So we're going to be saying, but we're not quite at 1. We cannot get to 1. So we're going to range from open on the 1 and what else are we going to range from? Well, what if X is 1, right? We can't do 0. But what if X, instead of being a really big number, it's a, again, small in the sense that when we have square, it doesn't matter if it's positive or negative. We want to have a number that is smallest possible output from a square, which in this case looks like we can do, well, we can do fractions also. We can technically probably get a pretty big output. So let's say we can have, let's say 0.05 times 0.05. That's 0.0025. And 1 divided by 0.0025 is 400 plus 1. So we can get a very large number, right? All we have to do is make these tiny numbers. So for instance, if we say X is, let me show you an example here. 0.05, so then we're going to say 1 over 0.05 squared, which is equal to 1 over 0.025, which is equal to 400. There's 400 of 0.0025 in 1. So then we're going to say 400 plus 1 is 401. So we could, in principle, as long as we go the opposite route, instead of going very big, we can get an infinitesimally small number. We can get 4 billion, 4 million, 4 trillion. So we're going to say this is going to range to infinity. Yeah, that's how my interval here, my understanding of it. Let's see if I got that right. Okay. And let's see how they solve this. Hang on a minute. The range, the domain, yeah, I got the domain here. To find the range of f, we need to find all the values of y for which there exists a real number where x is not equal to 0. So basically, so here's how they did it here. We took the equation, and we're just going to say 1 over x squared plus 1 is equal to y. And we're just going to solve that, okay? So then we're going to say, we have to solve in terms of x. So we're going to say minus 1, minus 1. So we have 1 over x squared is equal to y minus 1. We're going to square root it. So now we have 1 over x is equal to square root of y minus 1. And then we're going to trade places here. So it's going to be 1 over square root of y minus 1 is equal to x. And it should be plus minus because of the fact that we did the square root. So, yeah. So, and that is going to be the range. And in this case, the range is going to be, where is this a valid solution? So basically, the range can be where, well, now here we're going to get exactly the same thing that I got, right? I went about it a different way, but we're going to get the same result. Where does this break down? Where does square root of y minus 1 break down? Y cannot be 1 because if 1 minus 1 square root is equal to 0, that's acceptable. But what is not acceptable is 1 divided by 0, right? So that's the only point where it breaks down. And then if we can go with y. Now, the other thing is y can't be less than 1 also, because then we're going to have, let's say y is negative 2 minus 1, which is equal to negative 3 square root, not allowed. So we can't do that. So y cannot be less than 1. So y is going to range from 1, but it has to be greater than 1, cannot be 1, and it's going to go up to infinity. So we can go 2, for example. Let's say 2 minus 1 is equal to root 1, which is equal to 1 over 1. That's acceptable. That gives us 1. So yeah, the way I wrote it is it ranges from 1 to infinity. Infinity is going to be open on its end, of course. And on the 1, we cannot have 1, so it's open on this end. The other way to write it would be y such that y is greater than 1. That's another simple way of doing it. You pick whichever way you like to write it. Okay, and finally, we have one more to solve here. We're going to evaluate this one. We're going to write the function. And g of x is equal to 1 over x. And we're going to evaluate what is the composite of f and g such that x... Okay. Well, we did this earlier, but we did g of f. Now we're going to do f of g of 4. And also what is composite of f and g of negative 1/2. We did this, but we did it with g of f. Now it's f of g. So f of g looks like this. So in this case, 4. So we're going to write this as f of g of 4 So we're going to write the f function. And inside the f function, we're going to write the g, and the g input is given to us as 4. So that's going to be 8 plus 1, 9. Okay? Now, if you look at that, what is our, well, okay. This is our domain. This is our range. Input, output. All right? Now, well, let's do the composite of f of g of negative 1/2. So again, we're going to write f, then we're going to write the g function, and for the g function input, so the f function input is the g function, and the g function input is the negative 1/2. So we write the f function input. Inside it, we write the g function input. And hold up, I made a mistake there. it is actually like this. That's because the g function is 1 over x. It's not x. So in this case, it is for, how did I get 8? Okay, wow, what a mess. Let me fix that. Okay, it is 1/16 plus 1, which is equal to 1/16 plus 16/16, which is equal to 17/16. There we go. Because 1/4 times 1/4 is 1/16. We're just going to add 1. Now, we have our f function, and inside that we have our g function, and inside the g function we have the input. So this is probably a more accurate picture. Let me actually just take a minute here to draw a much nicer picture here for us. So we're going to have our f function, which the x input, we're just going to put that as parentheses, right? This is going to represent our input of the f function. Inside that, we have the input of, we have the g function with its input, and inside that is the input given to us, the domain, which is -1/2. So now we have -1/2 squared plus 1. Okay, so, well, let's see here. We have -1/2. We could actually do this. We can flip it and make it negative, because it's 1 over -1/2, which is the same thing as 1 over 2 negative. And now all I did there is I simply rearranged it. This right here, 1 over -1/2, is the same thing as -2. Okay, it's just another way of writing it. So we're going to say this -2 over 1, or -2 squared, plus 1. So that's going to give us 4 plus 1, which is equal to 5. So our domain, -1/2, and our range is 5. And let's just check, see how I did here. Yeah, that is correct on both accounts. All right, and then we have, okay, before we go, we're going to finish up with a check your work 1.5, and then we're going to stop and do 1.8 next time. So it's going to be 1.8, 1.9, and that carries us into 111. So we should be able to get through pretty quickly. It's about 4 pages till we hit the exercise of section 1.1. Okay, and those go on for a while. Wow, we have like 6, 7 pages. We have a lot of, we're going to be doing exercise for a while. We're in this chapter for a while. Yeah, so let's do our example. And this is example 1.5, and we're going to say, let f of x be equal to 2 minus 5x. So that's our function. And g of x, we're going to let that be root x. Okay? We're going to say find f of g. And I'm guessing they want the domain and range. They're not specifying that, but we're going to get the domain and range while we're at it. All right, so we're going to take our f of x. We're going to put our g of x in it. And so that is going to be here. We're going to say 2 minus 5. And inside that, we're going to put our g of x, which is root x. All right, 2 minus 5 root of x. And now, so we have that. Okay, so what can we do with this? Well, let's see here. We cannot have a negative number. We can have 0. The range is going to be here. So basically, let's just do it this way. We're going to say 2 minus 5 root x is equal to 0. We want to know where that breaks down. So, but the one thing is, all right, let me think about this for a minute. Let me take a different approach. We want to know fundamentally where this breaks down. Forgetting all of that, what we really want to know is where this breaks down. Or more specifically, that's okay, where this is invalid, where this is -1 or something like that. So we want to know where this is not in the real set. That's what we really want to know, because then we know where it breaks down. And of course, we know that anything if x such that x is going to be less than 0. And that's basically it. I'm forgetting about all this stuff out here. If x is, let's say, -0.01, it doesn't matter. You can't square root that. We can square it 0. It's cool. If we squared 0, it's going to be 0 times 5 is 0. The result will be 2. That's all valid. So this is going to be our domain. And what is our range? Okay. So this is our input. X has to be such that x... Oh, wait a minute. I wrote that wrong. Wow. It's really impressive how wrong I can be sometimes. All right. Such that x can be 0, and x has to be greater than 0. So x is greater than or equal to 0. X can be 0. That's fine. X can be 1, 2, 3, 4, whatever. That's fine. Not all those numbers are totally valid. X can be half. X can be a fifth. It can be a tenth. It can be a millionth. But it cannot be less than 0. So that's fine. What is going to be our range? All right, so we're going to say 2 minus 5 root x is equal to y. And we're going to say minus 2 minus 2. And then we're going to say, we're going to divide this by -5 divided by -5. So now we have root x is equal to y minus 2. And the -5, let's get rid of that. So that's going to be -y plus 2 over 5. And then we're going to square this. And that's going to be, this is squared. So we're going to say x is equal to, make sure I'm doing this right, plus minus -y plus 2 squared over 5. And where does that break down? I don't think it breaks down. Y can be any number, really. So what is, let me just review this. Does that really work? Can we get any number y as an output? Can we get any output with our constraints? So y, let's say if y is 10, right? It'll be -10 plus 2. So it doesn't matter. The output's always going to be positive, except for the fact that it's plus or minus. But in principle, we can get, and what is the smallest number we can get here? The smallest number, it would be, y would be, let's see here. I guess we can get y is -2. -2 plus 2 is 0. 0 divided by 5. Let's see here. 0 divided by, that should just be 0. Okay, so that's 0 squared. So yeah, that's a valid output. 0 divided by 5, 0 divided by anything is still 0. So if y was 2, and if we were to go less, say, no, it's going to be, if y was 0 itself, that would be 2/5 squared. That's 4/10, and then plus or minus. Let me see here. If we have, oh, right. So, right. We should be able to get pretty much, we can't get a, wait a minute. So, hold on. Can we get any number output? So, it's plus or minus something divided by 5 and the square root. So, in principle, if we wanted to say get like 100, right? We would have to go with this. The root x would have to be something like 100, and then square root of that is 10 times 5 is 50, or it would have to be more than whatever. But essentially, yeah, we get a large number square rooted times 5. It would have to, we would need 20, so it would be like 400. Root 400 is 20 times 5 is 100 minus, it's negative 100 minus 2. So we do have a limit here, and maybe I didn't do that portion of it, the y portion of it, right. Let me do that part again. I do feel that we are constrained, since the output has to be positive, that what if x comes out like a really, if we have a square root that comes out with a very small number, like 0.02, multiply that by 5, so that can be a tiny number. So we in principle can get, like, let's say 0.000005 is our output from the square root, okay, and then times 5, so that's going to be a very small number, and then subtract that from 2, so we are it's like 1.9999.75. So essentially 2, y is going to range from 2, and if we went with a small number, so it's going to be range, y is going to go from positive 2 to, positive 2 to, and if we got like a really large number, let's say like, I don't know, like say 10,000, so that's going to be 100 times 5 is 500 minus 2, it's negative 498. What is 100,000, 100 million? Again, you're still getting results to where progressively larger negative numbers. So we're going to say negative infinity. So the range of y and the range. So yeah, the domain of x has to be greater than or equal to 0, and the range is going to be from 2 to negative infinity. And one way to see this, if so, x can't be negative, right? And any positive number times 5 is gonna be a positive, or is gonna be a negative number that subtracts some portion out of 2, even if it's a tiny portion. So the closest thing we can get is we can actually make x equal to 0. So that's going to be root 0 is equal to 0 times negative 5 is 0. 2 minus 0 is equal to 2. So it will range from 2 to negative infinity for the range. We can have negative 2. Or sorry, we could have a whole 2. And yeah, so that's how I'm going to go about it. All right. Let's take a look here. That was 1.5. And let's see here. Yeah, they didn't do domain or range, and I suspect that they wouldn't, but I wanted to push myself and try that. This is it. That's all they wanted to see. So that was fine. Okay, so the stuff that we did, the domain, the range, that stuff was, it was great that we did that. It's important to do these things so that you can learn and grow and so forth. Anyways, let me just see if I can move this up a little bit here. But that's going to be it for tonight. I am going to go to bed now. So, yeah, we made some more progress in our calculus. We are now in page 24, halfway through it. So, yeah, we're flying along here. All right, that's it for tonight's stream. I will see you next time.